Good afternoon, everyone. I'm Pooya Nikbakht, graduate student from University of Manitoba, Canada. I will present a summary of our results on the fault-tolerant online bin packing. The co-author of the paper is Dr. Shahin Kamali, an assistant professor of the University of Manitoba. In this talk, we first start with an introduction on the classic bin packing and some basic concepts that we will need throughout. Next, we will see what server consolidation is and how it can be modeled by the fault-tolerant variant of bin packing. Then we generalize one of the more practical existing models for this problem and introduce an online algorithm called harmonic stretch. And finally, in the last part, we show our algorithm achieves an asymptotic competitive ratio of at most 1.75. Bin packing is a well-known optimization problem in which the input is a multi-set of items of various sizes in range 0 to 1. The goal is to pack these items into a minimum number of bins of capacity 1. So by cost of an algorithm, we simply mean the number of bins that have been used by the algorithm to pack all the input items. Sometimes an item is also presented just by a number that represents its size. Classic bin packing and many of its variants are known to be incomplete, and as a result, we are interested in approximation solutions that are polynomial at the expense of optimality. Such approximation algorithm can be studied under two categories: offline algorithms and online algorithms. Offline algorithms have the whole inputs in hand before packing them. On the other hand, online algorithms receive the items one by one and make a decision for them without any knowledge about the upcoming items. This decision for the received item can be either placing it in an already open bin or opening a new bin and placing the item into the new bin. Notice that the algorithm cannot relocate the items after this decision. To compare the algorithms in terms of their worst-case performance, we use approximation ratio for offline algorithms and competitive ratio for online algorithms. Let opt be an optimal offline solution for an input sigma. We say an offline algorithm has an approximation ratio R if for any input sigma we could write custom algorithm is at most R times cost of opt. If the right side of the inequality has been added to a constant C, then the R is called the asymptotic approximation ratio of the algorithm. The reason for calling it asymptotic is that if we only consider the inputs for which the cost of opt is asymptotically large, then we could ignore the constant C and write the same inequality as before. Competitive ratio and asymptotic competitive ratio of an online algorithm are also defined exactly in the same way. The only thing to notice is that we are comparing the online algorithm to an optimal solution which is offline, in the sense that opt has the whole input in advance. Our focus in this work is on the online setting and therefore on the asymptotic competitive analysis. In the online setting of bin packing, we know that no online algorithm can reach an asymptotic competitive ratio smaller than 1.542. And the best existing online algorithm has an asymptotic ratio of at most 1.578. So there is still a gap and the problem is still open. Server consolidation is one important application of bin packing in the cloud. Assume we have some data of different workloads on different servers. These servers might have different powers and capacities. The data here can be, for example, an application or a database on the server. We usually call it a tenant of the server. By workload of each tenant, we mean a combination of resources that it takes from the server. Resources like CPU, storage, memory, and so on. We assume that we are able to calculate and assign a single number to each tenant as its workload. In server consolidation, the goal is to transfer or consolidate all these tenants into some servers of identical capacity. And of course, we want to use the minimum number of such servers to minimum the cost. This problem can be modeled by bin packing. Items of different sizes in bin packing represent tenants of different workloads. and bins of unique capacity represent the servers of identical capacity. Hosting and cloud computing platform providers such as Amazon EC2 also use server consolidation to minimize the number of servers they use for their services. The client requests for hosting their tenants are made sequentially and over time, and this gives an online nature to this problem, and that's why we have studied only the online variant of the problem. The main challenge is that servers fail on a regular basis. And if a tenant is placed only in a single server, the failure of that server makes the service unavailable. To avoid this situation, there are replicated tenants in multiple servers. More precisely, in a fault-tolerant approach, if we want all the tenants to remain available in case of failure of up to F servers, it is necessary to keep at least F+1 replicas or copies of each tenant in F+1 different servers. Among these F+1 replicas, at any given time, one available replica works as a primary replica and responds to the service request for that tenant, and the remaining replicas stay idle as a standby replicas, just in anticipation of server failures. If the server that hosts the primary replica fails, one of the standby replicas are selected to become the new primary replica and makes the service available again. Some existing models assume that the workload number of the primary replica is the same as that of the standby replicas. But in practice, the primary replicas usually take more resources. For example, assume the tenant is a web application. Its primary replica takes different resources such as CPU, storage, and memory to run on the server. This is why the standby replicas are not running on the servers and might just take some storage from the servers. This brings us to a more practical model where a tenant with workload A has a primary replica of size A and F standby replicas of size A over eta, where eta is some parameter larger than 1. In this model, when a server that hosts the primary replica fails, a standby replica is selected to become the new primary, and its size is expanded from A over eta to A. So altogether, we have an online sequence of items or tenants of different size and two parameters F and eta as the input, and we want to pack one primary replica and F standby replicas of each item into bins of unit capacity. Servers might fail, and our packing should be valid in the sense that at any given time, the primary replica of every item should be available in a non-fail bin. Here we show an example of an invalid packing. Consider the following sequence and two parameters F and eta as the input. The first item, 0.4, comes, and because the parameter F is 2, we need to pack one primary replica together with two standby replicas of the item. The primary size is equal to the item size, that is 0.4, and the size of each standby replica is equal to the size of the item divided by parameter eta, which is 2 here. So the standby replicas here, each has a size 0.2. And assume the next items become packed as follows. And this is the final packing for this input. Because parameter F is 2, up to 2 bins might fail. Assume bin number 4 fails. Because it was hosting a primary replica of item 0.6, one of its backup should be selected to become the new primary. The algorithm cannot select the backup in bin B3 because when it expands to the primary size, the bin overflows. So it has to select the backup in B2, and it's expanded without a bin overflow. Next, assume bin B1 also fails. There are 3 primary replicas in it, and a backup of each of them should be selected to replace their failed services. For item 0.4, the backup in B2 cannot be selected. So the other one has to be chosen. And for the next item, however, the algorithm is left with no options because the expansion of any of them causes an overflow in their bins. So regardless of what adjustment strategy the algorithm takes, such packing is invalid when f is equal to 2. All existing valid algorithms for this model assume that first all items of the online sequence are packed, and then a set of up to f bins fail simultaneously. The best algorithm under this assumption has an asymptotic competitive ratio of at most 2. However, in a more realistic setting, first of all, some bins might fail and later recover again. Secondly, all failures do not happen simultaneously, in the sense that it might be the case that after failure and recovery of some servers, some new tenants are added to the available servers, and later, some new servers fail again. So we add these 2 more realistic assumptions to the existing models, and for that, introduce an algorithm called harmonic stretch. The algorithm classifies both primary and standby replicas based on their sizes. There are 7 classes for primary replicas, and 6 Eto+1 classes for standby replicas. An item that has a primary replica of class I and a standby replica of class J is called an IJ item. When I and J are both the last classes of replicas, the item is called a small item. And other items are called regular items. The algorithms pack regular and small items slightly differently. Regular IJ items are packed separately for each pair of IJ. For example, 1-1 items are packed in separate bins, so are 1-2 items, and so on. To pack the regular items of class I and J, for a certain pair of I and J, the algorithm maintains groups of bins. Each group is formed by the same constant number of bins, which is a function of I, J, and F. At any given time, there is one active group, and the items are packed into it. At some point, the active group becomes complete, and the replicas of the new items cannot fit into it anymore. So, a new group of empty bins is created and becomes the new active group. Each group of IJ items consists of J primary bins and I sets of F standby bins. Here we are illustrating the group structure for some examples value of IJF when I is equal to 2, J equal to 4, and F is 3. Primary replicas are packed only into primary bins, and standby replicas goes into standby bins. In each primary bin, there are I spots for I primary replicas of class I, and in each standby bin, there are J spots for J standby replicas of class J. With J spots in the standby bins, a reserved empty space is left in the bin. This reserved space guarantees that one standby replica of class J has enough space to expand and become as large as a primary replica of class I, which is its primary partner, in case of a failure. To pack one primary replica and F standby replicas of each item, the algorithm placed the standby replicas in the first spots in the first set of F bins, and the primary replica is placed in the first spot in the first row of spots in the primary bins. The next primary replicas fill the spots of the first row in primary bins, and their standby replicas goes to the first set of F bins. And this continues until all the spots in the first row of primary bins are filled, and the next primary replicas are placed in the second row, while their backups fill the second set of standby bins. As we see, such packing strategy generates F mirroring or identical standby bins corresponding to each row of primary replicas. Our packing strategy actually has some characteristics that we use for the adjustment strategy in case of bin failures. The first characteristic is that because all replicas of each item are placed in the same group, bin failures are also handled inside each group separately. The second characteristic is that each standby bin has enough space for the expansion of exactly one replica. And the last characteristic is that each primary bin shares exactly one item with each set of F standby bins. With these characteristics, we apply the following adjustment strategy. When up to F primary bins fail, F failed primary replicas of the first row are mapped into the F standby replicas in the first set of mirroring bins. And the F primary replicas in the next row are mapped into the second set of F mirroring bins, and so on. If a previously failed bin is recovered, both primary and its corresponding expanded backup replicas get their original status, in the sense that the original primary replica become available and their expanded standby replicas shrink and become idle replicas again. So far we've just talked about packing regular items, and here we briefly give the intuition behind packing small items. To pack primary and standby small replicas, we first merge a consecutive number of them until their total size reaches a certain value. The merged replicas are called super-replicas. These super-replicas have sizes similar to regular replicas, so we could use an almost similar approach to pack a certain number of them into groups of bins, similar to what we did for regular items. And finally, we analyze our algorithm in terms of asymptotic competitive ratio. For that, we use a weighting argument and show that asymptotic competitive ratio of the harmonic stretch algorithm is at most 1.75. The steps of weighting argument are as follows. We first assign a weight to replicas of each class. All primary replicas of a regular class I has a weight of 1 over I, and similarly, all standby replicas of a class J has a weight equal to 1 over J. In the next step, we show that the total weight of replicas in each algorithm's bin, except possibly constant number of them, is at least 1. To see that, it's enough to see that in each primary bin we had I replicas, each of weight 1 over I, and in each standby bin we had J standby replicas, each of weight 1 over J. When each bin has a weight of at least 1, we could conclude that the total number of bins used by the algorithm is at most equal to the total weight of all items in all bins. In the third and last step, we show that the total weight of replicas in any bin of an optimal packing is at most 1.75. And this implies that the total number of bins used by the optimal solution is at least the total weight of all items divided by 1.75. So bringing all together, we showed that the algorithm used at most as many bins as the total weight of items, and an optimal solution opens at least as many bins as the total weight of items divided by 1.75. So the ratio between the cost of our algorithm and cost of the optimal solution is upper bounded by 1.75, which completes our proof. That was a summary of our work, and here are some references that we referred to throughout the slides. And thanks everybody for listening to my talk.